You're so right about the weather. I'm from South Wales. In Wales, it rains the whole time. It is a very beautiful part of the world if you have an umbrella, but you have to have the umbrella, unfortunately. Thank you all for coming. It's my second time at Code Camp. I was here last year. I had a great time last year, so jumped at the chance to come back. I'd like to draw your attention to this first quote. The reason will become apparent. But to paraphrase, if you were an alien looking down at the Earth from space, you would be forgiven for thinking that cities were the predominant life form on Earth, and humans just the gut biome of the cities. The reason for this quote will become apparent, I hope. So we heard from Michael Feathers just a short while ago about what's happening at the sort of cutting edge of machine learning with things like large language models and ChatGPT. And actually, I'm going to be talking a little bit today about what's happening at the sort of bleeding edge of research into organizational design, into team structures, and how we optimize our organizations as they grow and scale, and how that relates to software architecture and team structures and things. So I hope that's okay. There are some graphs. Don't think there are any equations, so you're okay, I hope. There might be one equation, I can't remember, but I think there are definitely some graphs, so I hope you're okay with some lines. So this is my topic. I'm going to start off by introducing, I guess, why I'm interested in this topic. So way back when, myself and Martin Fowler, who incidentally I did go for a sleepover at his house, if you know Martin Fowler. I'm one of the few people who can say I've done that. It was the only way he could get me to write up the microservices ideas was to actually go and stay in his house. So I went and stayed in Boston. And at the start of our paper, we wrote this. We cannot say that there is a formal definition of the microservices architectural style, but we sort of collected together a set of characteristics. And these were the characteristics of the things that we were seeing out in the wild. We sort of harvested these characteristics of things that we were seeing that were working around the world on many, many different projects, from small startups to scale-ups to giant unicorns, from organizations just starting on Greenfield through to the Guardian newspaper, through to Netflix, and everywhere in between. We were seeing organizations adopting a new way of building software based on what we sort of describe as these characteristics. Now, that was 2014, we wrote this up. So the question is, what have I been doing the last 10 years or so? And that's really what this talk is about. It's about my interest and my further work and research and deeper understanding, I think, of what goes to make up the sort of underlying principles behind these microservice characteristics. In particular, there's a set here which are related to things like decentralization. They're related to how do we break big things up and turn them into smaller things so we can solve smaller problems, not just bigger problems. How do we push decision-making down to teams? How do we run teams as long-lived product teams who build and run software rather than as short-lived project teams? So there's a lot of stuff in here that talks to this idea of decentralization. And so over the years, I've been thinking, why is it that this form of building software, this form of software architecture, this paradigm, this style, why is it eaten the world? Or why has it been so widely successful? Or some might say unsuccessful. That's fine. You're doing it wrong. It's definitely successful. So that's what this is about. It's about the underlying ideas that I think go to make up the microservices architectural style, why it works, and the sort of underlying characteristics of the team structures and organizational designs that can help make these things work. So first of all, I'm going to introduce the idea of team topologies. So team topologies was a book written 2 years ago, or 3 years ago, which is, in my opinion, immediately become canon. I'm not sure if people in the room have come across team topologies. I'll show the cover in a moment. But I think it's one of the most important works in the space of what we do for a long, long time, probably up there with continuous delivery and COF working effectively with legacy code. He's not even listening over there. Now, I was lucky enough to be at a symposium some time ago, and at that symposium, there was a gentleman there who said something interesting. He said this about Amazon. He was working for AWS at the time, and he said, it's really strange, because at AWS, the bigger we get, the easier it becomes to get bigger. The faster we get, the easier it is to write software, the faster we get. The more teams we add, the easier it is for us to add more teams at AWS. In fact, he went on to say, the only limit to the number of product teams that we can add, the only limit is the people we can hire, right? If we could hire an infinite number of people, we could spin up an infinite number of product teams. I'm exaggerating slightly for effect, slightly hyperbolic, but not much. Now, I guess I'll ask a question. Who in the room has a similar experience at work, that as you get bigger, it's easier to get bigger? You put your hand up if it is. Blimey, there's a few people who can say that. That's awesome. That's awesome. Because the majority of folk you ask this to, they'll say, well, no, as we get bigger, things tend to slow down, right? As the organization gets bigger, we slow down. As the number of teams we add gets bigger, we tend to slow down. And in fact, you know, that's kind of the sort of standard, I guess, the received wisdom in the industry. Now, my idea of what makes a good team and what the purpose of a team building software is, I take it from Daniel Tuhor's North. He's got this lovely phrase he uses. So the purpose of a team is to safely and sustainably reduce the lead time to value. Which brings me to the ideas behind, underlying some of the team topologies work, which is this idea of flow and value, and delivery of value. But what is value? When Daniel North, Tuhor's North says, safely and sustainably reduce the lead time to value, what does he mean by value? So when I think of value, what are we delivering? Well, value can mean all sorts of stuff to different people. Value can mean things to us as software developers, as knowledge workers, right? Delivering software that produces value for our customers or end users. Value can be an orange shipped from a farm to a shop. Basically, stuff, right? Value, I think of as the delivery of stuff that has value to people, to teams. Generally, you know, it could be physical stuff, it could be knowledge-related stuff, it could be information that progresses through a series of processes, becoming more valuable until it ends up in the hands of our customers as software. Or it could be physical goods going through a manufacturing chain and ending up as a car, which we then drive home from a dealer. It's basically stuff. Basically, squint, and if you sort of think about it, knowledge work, what we do as software developers, when we're working in a team, we're taking requirements and we're passing them through a series of value-adding activities. So we're developing software, we're testing software, we're deploying software, and finally it's earning money. It's the same thing as when essentially a factory is assembling a set of goods. We're taking things that have less value, increasing their value by doing work to them. So in a factory, you know, we'll take stuff that's raw materials, gradually build it up into more valuable things until you know, it can be sold or delivered to our customers. The same thing happens when we build software. We're basically taking something that has lesser value, maybe an idea, and turning it into something concrete that's going to earn money. Basically, we take raw materials and turn it into a thing. I'll give you an example of this. I was very lucky to work for a clothing retailer in northern Spain, in A Coruña, a massive clothing retailer, one of the biggest in the world. And they are amazing at optimizing their time from designing a piece of clothing to getting it on the shelves to be sold. Right, they're world class at this. In fact, they will go from the designer putting the pen down where they've been sketching, 15 days later, that design is being sold in shops around the world. I mean, that's amazing, you know, the delivery of value through that value chain, through the supply chain, and into shops in 15 days. But generally, most organizations, when we're thinking about knowledge work, they don't have the ability to do that quickly. Now, this is a value stream map from an organization I was working in some time ago. As we can see up here, well, there's lots and lots of different... Is this working? Yeah. Working there. Is it working up there? No, not really. So over this side, we've got sort of requirements gathering and elucidation and all that stuff. In the middle, I've no idea what this stuff is. Data architects doing data architecty things. We've then got someone in the middle. There's one little orange post-it in this box here That's someone writing code. That's the code being written. And all of this is integration testing, user acceptance testing, kind of performance testing, regression testing, and so on. This is an organization that's built up a set of processes and constraints over about 200 years of existence. And what they've ended up with is this really long process of going from idea through to production, going through this value stream, adding more value, more information, and then gradually putting something into production. Things take quite a long time in this process. It doesn't matter if you're the developer writing some code in that little post-it in the middle, you could write that code infinitely fast. ChatGPT could be writing your code for you, right? But it doesn't matter. It's still going to take you 9 months to see any value because the work has to go through the rest of the value chain. So things take time generally in bigger organizations. Now, the interesting thing about team topologies is it's a way of looking at your organization and splitting up your teams and splitting up your value streams in a way that helps with this delivery, this improvement in flow. So this is the book, Team Topologies, by Matt Skelton and Manuel Pais. They're old sort of acquaintances of mine from the London continuous delivery community. And in this, they talk about how to build team structures that allow you to align your teams with the maximum delivery of value, the improvement of flow of delivering requirements, delivering working software to your customers. And they describe 4 different team shapes that help do that. They describe like a value streamlined team. They describe platform teams. They talk about enabling teams, and they talk about complicated subsystem teams. Now, I'll talk about a value stream-aligned team. I did some work some time ago with the recommendations team from the Amazon.com website. They're based in Edinburgh in the UK, or they were at the time. And the interesting thing about that team is they were aligned directly to their end user, to the customer. So the recommendation engine they were building, when they were producing results, the results were shown below the fold on the Amazon website. The HTML they were building were included on the website. They had a direct line of sight, value stream, essentially, from what they were doing to their customer. And it enabled them to make decisions really quickly. They could operate as a proper product team, making proper product-oriented decisions. And that's an idea of a stream-aligned team. Other teams like enabling teams. So, what happens if you've got a set of limited resources like InfoSec people or maybe some DevOps folk? Well, you can use them in an enabling role to act as consultants to the rest of the organization, to the other value stream-aligned teams. Platform engineering teams, these are often sort of rebadged operations teams. That's not what we're talking about here. Platform engineering teams offering self-service access to infrastructure, self-service access to tooling that enables the rest of the organization to get stuff done more quickly, more effectively. That's what platform-aligned team. And then complicated subsystem team, we've always got a bunch of quants or risk people sitting somewhere who need specialist skills, that kind of thing. So that's fundamentally team topologies. It's a way of thinking about team structures. It gives us a ubiquitous language, if you like, to talk to each other about how we structure our teams and our organizations. And that's why I think, personally, it's so useful, because it's this ubiquitous language. Brings me on to the next topic, which is the idea of software architecture and complexity. Now, I mentioned this idea of Amazon going faster, Amazon having the ability to get faster the more people they add. So the more teams they add, the faster they get. The more teams they add, the easier it is to add more teams. The more software they build, the easier it is for them to build more software. I was lucky enough to be at an event some time ago now, 5 years ago. It's a tough job, but someone's got to do it. So I was at an event in the Caribbean on the island of Anguilla. And this is myself on Shoal Bay East, one of the top 10 beaches in the world, sorry, everyone, for a week-long symposium. And we talked about all sorts of interesting cutting-edge stuff. And one of the people in this picture in the middle, that's Adrian Cockcroft. He's the guy from Netflix who helped them transition to the cloud, famously. And this, ladies and gentlemen, is a gentleman called Melvin Conway. I don't know if anyone in the room has come across the concept of Conway's Law. This has become very, very popular. Hands going up. Hands up for Conway's Law. He exists. He's a real person. There weren't that many hands going up, so I'll just explain what Conway's Law is. So Conway's Law was back, he sort of wrote this down after a bunch of research back in the late 60s. And he sort of found in his research that the structure of the software that an organization builds mirrors the organizational design of the people building the software. So depending on your team structure, you'll end up with a software architecture or set of systems that mimic that team structure. And this over time was, there was further research done by Microsoft in conjunction with MIT. There's a paper called Test of the Mirroring Hypothesis. That's what the alternate name for Conway's law is. And they found that this held, even down to the way Microsoft's own internal products were being built. So the operating system, Windows, and also their Office products. They found that the mirroring hypothesis held. This idea that the team structures you have is intrinsically linked with the structure of the software that you're building has been sort of picked up, I guess, quite widely in the last few years. And I was very lucky, again, to be hanging out with Mel. And we had like an open space one afternoon where we talked about the uses we'd put Conway's law to. And Adrian was talking about how they structured in Netflix around proximity of need of information. So if I'm in the UX team, I probably don't need to talk to the Cassandra folk that much. So they sit them miles away, right? But I do need to talk to the platform API team. So I'll sit next to the platform API team. So I've got this high bandwidth communication, optimizing the structure according to information flow, the flow of information within the organization. Now, as I said at the start of this, there was someone there from AWS who said this: the bigger we get, the easier it becomes to get bigger. Now, the recently late Fred Brooks, in the Mythical Man Month, he stated this, right? Adding manpower to a late software project generally makes it later. And the reason behind this is because as you add more people, the productivity gains you get from adding more people to a project, to a program, or to a product build, the productivity gains as you add more people get overtaken by the coordination cost of having those people on the team. You have to do more coordination the more people you have, and so things eventually start slowing down. And this is received wisdom, and it has been for decades in our industry. And this is decades-old advice. Which is why I was so intrigued by this idea that AWS, in particular, are able to go faster than potentially they should, or certainly my experience was at large organizations. So I ran some numbers, warning pseudograph. Actually, Andy Jatti showed a similar version of this 2 years ago at reInvent. This is a random graph. What it shows, basically, is a plot of Amazon revenue versus Amazon employee count. So as Amazon is doubling in size, the number of people it has, its revenue is going up. That's the important thing, 1.15. An exponent of 1 there would mean if it doubles in size, it doubles revenue. Because that exponent is bigger than 1, what it means for Amazon is as Amazon doubles in size, they more than double the revenue they're making. Effectively, they're making more money than they should. They're going essentially faster than they should. So I thought, well, that's interesting. The numbers seem to back this up. So I started digging deeper into why this might be the case for Amazon, and in particular AWS. So the interesting thing that happened with Amazon, we all know about this many years ago, 2004, Jeff Bezos, he sort of wrote this memo which had a bunch of points in which said, okay, we've got this big monolithic system written in, I can't think it was Barclay DB, and I can't remember the language at the time, it wasn't Perl. But we've got this big monolithic system, we've grown to Oracle databases, everything is integrated via the databases, things are slowing down. So he wrote a very famous memo in 2004 that said, we're going to do these things, and this is the future of Amazon, essentially. And these things that we're going to do include teams only communicating via interface. So we're not going to be communicating via database calls anymore, database to database integration. We have to go through an interface. So every team must have a set of interfaces that other teams can use in order to access whatever they're providing. Went further and said, those interfaces must be externalizable. We must be able to sell these things, right? They must be kind of tough and hardened to the extent that they could form a revenue stream in the future for the organization. And then he went on famously to use the phrase two pizza teams. We will structure such that no team can be bigger or should be bigger than two pizzas. And then he said, and if you don't do this, you're fired, right? I mean, EU labour law. You don't really get away with that, which is good, I think. But that was the gist of it. So what was he doing when he was sort of issuing these edicts? Well, I like to think of these as sort of forcing functions that he imposed on the organization, and therefore the team structure, and therefore the software architecture that they were building to improve flow, to improve the ability to get stuff done. So these, in essence, are forcing functions for flow. If you go back over them again, the first one, limiting interactions to nearby teams, a bit like I was saying with Netflix. The next one, isolating teams from one another. And then finally, this idea of scaling by adding smaller teams to, onto the side, if you like, so scaling by 2 pizza teams. These are forcing functions to improve the rate at which they can produce software. It, in fact, led to Amazon Web Services, right? I mean, this is the end result. AWS is a result of this structure, and then each team having to do what they referred to back in 2010 as undifferentiated heavy lifting. Right? Each team was having to procure everything. Each team was having to procure their own firewalls, et cetera, et cetera. So they extracted that into what became Amazon Web Services. And crucially, Amazon Web Services offered their services on a self-service basis, accessible via APIs, which were externalizable. And because of these things, they could sell them, right? And that's where AWS came from. They were able to sell these externalizable interfaces as AWS. Now, I touched a little bit on the importance of software architecture for things like how we structure the organization, how we deliver value more effectively. Touched a little bit on team topologies, team structures aligning with our customers, right? So we can more effectively deliver value to them. We also mentioned complexity in the title of this talk, which brings me on to the sort of more, I guess, bleeding edge concept of complex adaptive systems and complex adaptive systems theory. So complex adaptive systems came out of work that happened at Los Alamos, actually, in the sort of late 40s and early 50s and then 60s, and then was transferred to the Santa Fe Institute. It was started by a bunch of physicists, including a Nobel Prize winner called Murray Gell-Mann, and they were fascinated by the idea that we could get complexity from simplicity. What does it mean to be human? What does it mean for us to be so complex when we're built up from the individual components, which are subatomic particles? How do you get this emergent complexity, emergent behavior, which makes life or other complex systems? Over the course of the next sort of, I guess, 30 years or so, a bunch of further research was done into what people were sort of seeing in the real world, which corresponded to sort of oddities, if you like. Strange sort of coincidences that started popping up in the natural world between these things called complex adaptive systems. So here's an example of one of these oddities. All mammals share the same number of heartbeats in their lifetime, right? We have roughly the same number of heartbeats as a mouse and as an elephant as a blue whale. We also share the same blood pressure. Our blood pressure is the same as a mouse. Right? But what's the difference between a mouse and an elephant? Well, an elephant lives an awful lot longer than a mouse. We live an awful lot longer than a mouse. So something is whilst we've got some constant things happening, blood pressure and heartbeats, there's also some things that are changing. And that is, as you double the size of a mammal, the metabolic rate of the mammal basically goes up less than it should. So as you double the size of a mammal doesn't need to take in as many calories as it should, essentially. So you think you'd have to give a dog twice as much food as a cat. You don't, actually. You need to give it about 75% if the dog is twice the size of the cat. And the reason is because as you scale a mammal, the metabolic rate slows down. Elephants operate so slowly their cells don't develop cancer. They don't, as they don't split enough times, divide enough times to actually develop cancer over the years. So bigger animals operate much, much more slowly. Their metabolic rate is much, much slower than a mouse's metabolic rate. So there's this interesting scaling law, one of these oddities that's popped up in research into complex adaptive systems. Metabolic rate in mammals follows this scaling law, a straight line on a log-log graph with an exponent of 3/4. There's another oddity around organizations. As you double the size of a company, if you look at the data on NASDAQ, as you double the size of an organization, you don't double the amount of revenue it takes in. Actually, as you double the size of a company, you generally take in about 85% of the revenue that you should. You don't get 100% more revenue, you get 85% more. That's kind of a strange straight line in the graph as well. So you get this other scaling law that companies, as they double in size, their revenue scales with an exponent of 0.85. Cities have a similar weird scaling law going on, another oddity. As you double the size of a city, you don't have to spend twice as much money on infrastructure as you double the size of a city. Right? So as you double the size of a city, you don't have to spend like twice as much money on roads or on water pipes or on petrol stations. In fact, you only need about 85% of the petrol stations when you double the size of a city. And all of these are examples of scaling laws. And all of them are examples of scaling laws with an exponent less than 1. Now, I refer you back to Amazon. The Amazon graph is showing that their revenue is increasing with an exponent greater than 1. Right? They're making more money than they should. In this case, most companies make less money than they should. So what's going on? West said in the book Scale, which is a brilliant book, quantities that do not change when other parameters of the system change, they play a special role in science. Basically what he means is when you see oddities like this, straight lines on a graph, you should probably ask why. Right? There might be some underlying reason why these things are happening. And basically what he found is there's a scaling law operating in these cases called economies of scale. So linear scaling in the complex adaptive system, as you double the size of a thing, you double the size of the other thing. What we're seeing here, which are CFOs like economies of scale, is as you double the size of one thing, you get less than double the thing out. So sublinear scaling. And that's down to all of these things being examples of complex adaptive systems. Cities, mammals, basically everywhere you look are complex adaptive systems. The teams you work in, the organizations you work in, your family, the city you live in, all of these are complex adaptive systems. And complex adaptive systems, they sort of exhibit these properties. So the first is self-similarity. Our cells are the same as a mouse's cell. They also display self-organization. As we grow in the womb, there is no central orchestrator or conductor telling the human how to become a human. It just sort of emerges over time, self-organizing. And they're complex, so the whole is greater than the sum of the parts. If you take James and you put James in a blender, right, and you make James soup, it's not a nice idea, and then you pour James soup into a James-shaped mold, you don't get James anymore, right? You just get James soup in a James-shaped mold. There is something more to James, something more complex to James than James soup. And then you get this idea of emergent behavior. And emergent behavior means that you can't predict the behavior of the whole. You can't predict the behavior of James just by looking at the cells that make James up. And all of these systems I've described can be described are complex adaptive systems according to this definition. And moreover, all these oddities on the graphs can be explained by 3 principles. All these straight lines come down to 3 mathematical ideas. Excuse me. First is the idea of networks. In this case, hierarchical networks. Right? So space-filling, excuse me again, space-filling hierarchical networks. The second thing is this idea of an invariant terminating unit, a cell in a mammal, or a human in an organization doing work, or excuse me again, or a human in a city, the invariant terminating units. And then some form of feedback mechanism. So some form of optimizing the behavior of the complex adaptive system over time. All of these straight lines can be explained using these simple properties. And as I say, complex adaptive systems, they're everywhere. Everything we look at is a complex adaptive system. Everything that we look at today, the festival we're in, is itself a complex adaptive system. You could run this twice and get the same answer, the same things happening in the festival, right? Different things would happen. I have to drive this point home. Hierarchies imply scaling sublinearly, right? Whenever you have a hierarchical system, you get economies of scale. You get less out than you think you will, right? So hierarchies in mammals, as mammals grow, they explain why mammals' metabolic rates decrease. It's down to the depth of the circulatory system. A blue whale's got more arteries between its heart and the capillaries. And mathematically, that's enough to explain these patterns in nature. And then finally, Walmart and a convenience store. Basically, we're talking about self-similar things. We are the same as a mouse and as a whale. The only difference really is the emergent behavior of our giant brain. Which brings me on to, that's great, James, what the hell are you talking about? What's the relevance has this got to me? Well, the funny thing is that companies exhibit very similar properties to animals, right? And it's down to the same reasons. Right? Companies that have deep hierarchies exhibit the same properties as mammals that have deep hierarchies in their circulatory system. Companies' metabolic rates slow as the hierarchy increases. Things slow down. As you add more people, you tend to grow and grow hierarchies, and things get slower and slower. And it's just down to the hierarchy itself. The hierarchy can explain mathematically why things get slower. Why does revenue growth slow as size increases? It's for the same reason that metabolic rates slow as size increases. The depth of the hierarchy of the circulatory system, the depth of the hierarchy of the information networks operating in companies. The deeper the hierarchy, the further information has to flow, the slower things get. So bigger animals are more efficient. They don't need as many calories. And this is down to this thing in the circulatory system, and that's driven by evolution. The bigger companies are also more efficient. You don't need to buy twice as much network cable as you double the size of the office. Bizarre, but a true fact. You only need to buy about 85%. So they're more efficient, right? But because they get these hierarchies, they slow down. They both slow down. So I'm coming back to flow, and I mentioned about why this is, right? So if you look at this, the value stream map again, you can think of a value stream map as a slice through the information hierarchy of an organization, the path which, like value or the idea of value, has to flow from idea through into delivery into production. And the longer the value stream, the deeper the hierarchy, the slower things are naturally going to go. It's math. Essentially, what we tend to have in lots of these value streams is a bunch of queues that we put in place. I mean, I'm sure people in the room are using Jira. Like, Jira is essentially a queue of work. Jira is essentially, every time you see a queue, you're essentially blocking information flowing from one end of the information hierarchy to the other and causing things to slow down. And we tend to add more and more queues as we get bigger and bigger. So, as an example, in this value stream, we've got 5 manual testing stages taking months and months and months. Things getting slower and slower. If you like, adding queues into our system or adding all these process steps, it's like cholesterol buildup in our arteries, right? Things just slow down. Blood is not able to flow as quickly as possible. And in some cases, we deliberately give ourselves heart attacks. And I'll come on to that in a sec. So corporate metabolism. As companies scale, they add more and more processes, therefore things slow down. But we also deliberately block our corporate hierarchies. So it brings me to some practical advice. There's not much practical in here at the moment. So here's some practical advice. Read this book, Accelerate. It's awesome. It's the summary of the state of DevOps reports over the years. And in this, they identify a set of metrics you can use to essentially work out whether you're healthy or not. Work out whether your organization or your team is healthy or not. But here's a fun fact for you. Change request boards, and I use this word advisedly, predict low organizational performance. If you have change request boards or architecture review boards, it's a predictor of being in the low performing organizational set from the state of DevOps reports. That's pretty interesting, and it's because, if you think about it, every time you have to submit something to a change request board, everything has to stop. It's like literally stopping the flow of blood in your body, right? Things don't work out well. And then eventually it's released again. We're sort of putting back pressure up on the corporate circulatory system. So, practical advice. Can we actually understand how healthy organizations are? I think we can using the 4 key metrics. So the 4 key metrics is now 5 from Accelerate: mean time to recovery, cycle time, change failure rates, and the number of deploys per unit time. These are the equivalent of going to the doctors and having them check your blood pressure, your temperature, and your heart rate, right? They're basically indicators, leading indicators as to whether anything's wrong with you from a health perspective. And so what we can do is understand where we are according to the 4 key metrics and work to optimize them. But crucially, by optimizing the 4 key metrics, you'll only get as good as the hierarchy you're in. Because if you're in a hierarchy, there's nothing you can do about it. You're always going to hit a limit imposed by the hierarchy itself. So, understanding the effects of aging. You can use 4 key metrics as leading indicators like monitoring, heart rate, and blood pressure. But improvement is limited by the scaling laws. It's just math. It's literally, we can do the math. It's just doing the math. On to the next depressing bit, because probably most of us are in hierarchical organizations, sorry. Companies die, right? It turns out the half-life of an organization on the stock exchange is about 10.5 years. So every 10.5 years on the exchanges, you get 50% churn. Companies are taken over, they return to being private, they go bankrupt, et cetera, they merge. But fundamentally, organizations die in the same way that mammals die. And it's for the same reasons that mammals die, interestingly. What happens is, as organizations scale, they spend less and less money on the things that made them successful in the first place. So things like product development, research and development, bringing new things to market. And instead, that money is focused on keeping the company going. We spend more money in the company on, effectiveness drives and organizational redesigns and all the stuff that isn't actually to do with the thing the company's known for or the products it builds. We spend all this money just to keep the company going. And that's what happens as humans age or mammals age. More of the calorific intake, more of the energy we take in is spent on cell repair and repairing damage over time, and less on youthful enthusiasm and rock climbing and things. I don't know, I didn't rock climb. And then eventually, like mammals, companies die for the same reasons. They also add more and more processes and constraints over time. So things get gradually slower and slower and slower. Hierarchies get deeper and deeper and deeper, and then eventually organizations die. So, to summarize that really depressing section, hierarchical organizations, they gain economies of scale for infrastructure, but achieve sublinear revenue growth. Essentially, over time, the metabolic rate of the company reduces, and eventually the company dies. But there is good news, and this is the good news bit. This is the stuff you can do about this, because there's another scaling law that we can look to. And that's a scaling law called returns to scale. This is when you get more out than you should get, right? At the moment, we're getting less out than we think. There's a scaling law that says we can get more out. And superlinear scaling is what that is. And cities, as a complex adaptive system, exhibit both types of scaling law. So for innovation, wages, pollution, socioeconomic factors, cities exhibit returns to scale. You get higher wage growth as you double the size of a city, or more than double wage growth, in fact. You get more than double the number of patents. You get more than double the number of software developers and lawyers and number of professionals. But you also get more than double the amount of pollution, more than double the amount of disease. COVID spreads more quickly in bigger cities than it does in smaller ones, for example. But they also, as I say, display this economies of scale for infrastructure purposes. Right? And incidentally, if you've ever thought that if you go to a bigger city, people walk faster, they actually do. People walk faster in bigger cities. MIT did some research in conjunction with some of the mobile phone companies. They got a bunch of mobile phone data, and they found that as you double the size of a city, people walk faster up to the limits of how fast their legs can go. So I, for one, welcome my exoskeleton legs in the future. I'll be zipping around the place. But these are all sort of characteristics of a complex adaptive system known as a city. And the reason that cities exhibit returns to scale for socioeconomic effects is because these socioeconomic effects are dependent on a different type of network effect. So we talked about hierarchical networks driving economies of scale and sublinear growth. Small world networks, social networks, drive superlinear growth. So if you want more out than you put in, if you like, or than you should, social networks are the way to go. And the reason is because it's about the connections that people form with one another. And as you increase the size of a city or increase the size of a town, we get to associate with who we want. So if you're in a village of 100 people and you're a software developer, there might be another software developer in the room, in the city, or in the village. There probably isn't. If you're in a city the size of Bucharest, there's a ton of software developers that you can hang out with, right? And this is the thing that drives innovation. This is the thing that drives these socioeconomic effects being super linear in scale. This idea of basically forming relationships with the people you want to form relationships with. So, to drive this home, two types of scaling law. Economies of scale mathematically driven by hierarchies. Returns to scale driven by small world social networks. And the reason is that you can just plonk little social networks can sort of form next to one another without disruption causing in a hierarchical network. So as cities grow, they display economies of scale for infrastructure, and they gain returns to scale for socioeconomic factors. They rarely die. Essentially, cities are so successful because they get 115% of the stuff for 85% of the cost. Right? That's why cities are so successful. Now, other organizations out there growing like this, using this information to drive their own growth, right? Companies using small world network growth. I would argue ThoughtWorks was designed to do just that. Rather than scale via a single big office in each country, we scale by having multiple small offices so we can keep our communities small. We keep our communities to about 200 people per office, which means, I know that, Michael's into playing golf on a weekend, and I know the names of his children, for example, because over 200 people, you can't keep that many connections in your head. So, ThoughtWorks has been scaling via social network growth. The Spotify model, both of team structure and the way they're building software, their software architecture, right? You could argue the Spotify model is an example of trying to scale by small world network growth, via social networks. Small squads organized into loosely organized into I always get this wrong, into tribes, and then the tribes having just enough coordination across them in chapters and guilds in order to make them, effective, in order to make communication effective. But it's small world network growth. It's growing via these small units. Valve software. So Valve software leaked their internal employees handbook, or it was leaked, maybe. In the employees handbook, they actually call out the fact that they want to grow via small world network growth. Right? They're saying this is a deliberate thing we're going after because we believe this will make us go faster. And then finally, coming back to where we started, the curious case of Amazon and this strange graph with, curiously, the exponent of 1.15 on revenue growth, which is the same as you get for returns to scale driven by small world networks. It's the same number, the same exponent. So, as most organizations get bigger, it gets harder to get bigger. Things slow down. You add more processes, constraints. You add more hierarchies. Things get harder to build. The flow of value slows. It's harder to structure teams. But as Amazon gets bigger, it's easier for them to get bigger. And the reason is that they're able to just plonk new teams building new products next to each other, kind of decoupled and driven by the set of externalizable APIs that AWS and the infrastructure they've built offers them, right? So coming back to team topologies, one of the things I didn't call out as a forcing function for flow is this idea of being value stream aligned, having a direct line of sight to your customer. I think that's crucial. The second thing in team topologies is the idea of self-service access to tooling enabled by platform teams. And what that gives you is the ability to build these decoupled, to build smaller units of decoupled software in product teams and so on. So going back to these team topologies, if you haven't got this book or come across this book, it's brilliant. It gives us a common way of talking about a lot of the ideas I've been talking about today. So I guess to summarize, this has been my journey over the last sort of 10 years. This idea of decentralization, of breaking things up into smaller bits. Why does this work? And I think the ideas in complexity science behind complex adaptive systems point to why. It's because what we're trying to do is we're trying to create teams building software that is decoupled and cohesive from cohesive in and of itself and decoupled from other teams in the organizations, driven by social network growth, essentially. That's what we're talking about when we're saying push decisions down, create autonomy, create autonomous teams building microservices as products. Yeah, and just to drive this home, social network effects imply super exponential growth. Who doesn't want super exponential growth? Hierarchies slow metabolic rates. We should think about team shapes for improving the flow of value. And it doesn't necessarily have to be in software development organizations. Most organizations, I think, would exhibit the same effects if they organize this way. And then think about forcing functions for flow. What forcing functions can we use in our organization to improve the flow of value like Bezos did? I'm going to point this out at the end. So, you know the phrase, and I appreciate I'm 1 minute over, you know the phrase, it's not paranoia if they are actually out to get you. You come across this, right? If they are like out to get you, it's not paranoia, they're just genuinely out to get you. So Jeff Bezos is a patron of the Santa Fe Institute. He lives up the road in New Mexico, which is interesting. He's known this all along, or maybe he's known this all along, and has designed Amazon and AWS in this way, using these forcing functions. So as I say, this is cutting edge. This is research, this peer-reviewed research. It's summarized, a lot of it, in these books. And these are a lot of the papers that I reference as well behind these ideas. That's what I've been thinking about for 10 years. I know it's a bit... I'll be around for questions the rest of the day. Thank you very much for coming.